Hello everyone. In the last class, we started with the characteristic equation. What is the characteristic equation? It is nothing but an algebraic description of the next state table. When I say the next state table, it is nothing but characteristic table. In order to come with a characteristic equation, the first thing is come with a characteristic table. Once you have the characteristic table, with the help of K-map, simplify the expression, and whatever is a simplified expression, what you get, that is nothing but the characteristic equation for respective flip-flop. In the last class, we studied the character equation, how we derived for an SR flip-flop. Right? If you see here, like we have a function table. With the help of function table, we came with a characteristic table. And once we have the characteristic table, since we know about three variable, how to simplify a three variable K-map, we substituted the next state values what we have, and we simplified this equation. As I said here, for 1 yes is 1, R is 1, we take it as don't care condition. And what is the expression what you get here? What is the character equation for SR flip-flop? This is equal to yes or R bar Q, and SR is equal to 0. And this condition is a must. What it says is that we cannot have yes and R as logic 1 simultaneously. Right? We derived the character equation for SR flip-flop. Now we'll proceed with the character equation for other flip-flops. The next one what we have is JK flip-flop. How the JK flip-flop works. We know that when J is 0, K is 0, the next state, when the clock pulse is applied, the next state is equal to the previous state. Similarly, what we have when J is 0, K is 1, which is nothing but what? Reset state. Irrespective of the previous state, the next state is equal to 0. This you can consider as this something like this is nothing but an SR flip-flop. J stands for yes and K is for R, right? So that what we have when it is 0 and 1, this is a reset state. When J is 1, K is 0, what we have? This is a set state. Irrespective of the previous state, if J is 1, K is 0 and the clock pulse is applied, the next state is always equal to logic 1. Similarly, what we have? 1, 1. As I said here, the difference between SR flip-flop and JK flip-flop is, we know that in SR, when both S and R is 1, we have an undefined state, or right, in undefined state what we have. So that here in JK flip-flop, we have a defined state. So that when it is 1, 1, the next state is nothing but the complement of the previous state, right? Now, since we know the function table, with the help of function table, we can come with the characteristic table. Just a minute, I'm trying to come with an editor. Okay. Yeah. Now, how do you come with a characteristic table for this one? When J is 0, K is 0. Really what we have, J is 0, K is 0, right? And this is our previous state. Q is the previous state, Q plus is the next state. Now, what is the previous state value? What we have? 0, right? When both is J and K are 0, we know from the function table, when both are 0, the next state is equal to the next state what we have, right? The next state is equal to the previous state. So that what we have it now here, So that what we have, since the previous state is 0, the next state is also is equal to 0 here. Similarly 0 0, since the previous state is 1, the next state is 1 here, right? Similarly what we have 0 1, right? This is nothing but reset state irrespective of the previous state, right? Irrespective of the previous state, when k is 1, j is 0, what we have, the next state is what? Is always equal to 0. This is nothing but a reset state. Similarly what we have now, when j is 1, k is 0, j is 1 and k is 0, right? This is nothing but the set state. So that irrespective of the previous state, the next state is always equal to logic 1. Next what we have, j is 1 and k is 1. J is 1 and k. This is nothing but toggle, right? The next state is equal to the complement of the previous state. What is the previous state we have? 0. So that what is the next state we have it now? Here, as you can see, it is equal to 1, right? Similarly here, when j is 1, k is 1, the previous state is 1, so that the next state is equal to 0, right? Now, once you have the characteristic table, now come with a now substitute all these values, whatever you got in the characteristic table for the next state, the q plus what you have. Since there are 3 variables, j, k, and q, the previous state, this is, we have 8 cells, a 3 variable k map. We know it how to simplify this expression, right? And simplify this one, what we have? This is 1, 1, 1, and 1. We have 4 ones, so that we have substituted here, right? And we have here this one and this, right? Now, how do you simplify this one? This is 1 and 1, which is a common term what we get here now. You know that this is q bar, 1, 1, and 1. So that is j q bar. Similarly, for this one, these two are logically adjacent. So that what is simplified expression for this one? K bar q. So that what is the characteristic equation for a JK flip-flop? We have it is equal to q plus is equal to j q bar or K bar q. Right. Similarly, we'll go to the next one now. Now, similarly, we'll do it for D flip-flop. What is D flip-flop? D stands for data flip-flop. So that whatever the data you give, when you apply the clock pulse, the same data is given as an output. So that when the D is 0, when D is 0, when the clock pulse is applied, the output next state is equal to 0. Similarly, when it is 1, the next state is equal to 1. Now come with a characteristic table for this one. So that what we have D and we have previous state and we have a next state. So the 2 raised to 2 is 4. We have 4 input combinations. Now what we have, this is 0 0 0 1 1 0 and 1 1. So that what we have now, it is nothing but data flip-flop, right? It is nothing but data. So that what we have now here, right? Whatever you give as an input, that will be your next state. So that how do you simplify? Since it is 2 variables, what we have 4 cells. Substitute in the K map here. This is 1 and this is 1. So what is the expression what we have? It is T. You can know that the next state is nothing but, since it is data flip-flop, right? Whatever is an input, you get that as an output. So that it is entirely dependent on the input information what you give here, right? If it is 0, you get output as a 0. Similarly, if it is 1, the next state is 1 there, right? So that what is the characteristic equation for a D flip-flop? Q plus is equal to D. Next, we'll go to a T flip-flop. What is the T flip-flop? T stands for toggle. T stands for the toggle here. So that now what we have it now. Just a minute, we'll go to the next slide. Okay, so I've not changed this one. Everyone please make this change. This is a toggle flip-flop. Make this as right. Depending on this one, you can change this one here. Make this as a Q bar. I'll just write it here if possible. This you can write it as Q bar. I'll make this correction before sending to you guys. You get the complement of the previous state here. Right? This is T flip-flop. So that how you come with a characteristic table for this one. We have T, the previous state, and the next state. So that what we have 0, 0, is 0 and 1. When T is 0, 0, it is nothing but both are J and K are 0, 0, right? So that what we have, it is nothing but the previous state. If the previous state is 0, the next state is also 0. Similarly, if the previous state is 1, the next state is also 1. And when T is 1, as I said, it stands for toggle. So that both J and K are 1. When J and K are 1, the next state is nothing but the complement of the previous state. Here what we have it now, since it is 0 here, now what you get now, complement of the previous state will be 1. Here what we have, the previous state is 1 here, and what will be the complement of this one? It will be 0, right? Everyone understood this one, how to come with a characteristic table, right? Once we have the characteristic table, now draw the two variable K map, substitute the values, right? Now what we have it here, we cannot group it. We cannot group this mean term 1 and 2 because these two are not adjacent. So that what we have it now, so that this is nothing but T Q bar and this is T bar Q. So that what is the character equation what we have? The next state, Q plus is equal to T Q bar or T bar Q, right? This is nothing but what we have it is nothing but an XOR operation what we know, right? You can just by looking at this one, we know it's an odd function. It is 0, 1 and 1, 0, right? For this two condition, the output is 1, 1. For rest of the combination, it is a 0 here. So that what we have an expression here, it is nothing but an expression for an XOR, right? Everyone understood how to come with a characteristic equation. Here, the basic thing what you should know is, you should know the function table. If you know function table, you can come with a characteristic table. And once you have characteristic table, with the help of the K-map, simplify that one and come with a characteristic equation for respective flip-flops. Now we'll go to the next topic, which is registers. Now we'll understand what you mean by a register. We know a register a little bit. As the name says, register, it means that it is storing, right? Register. Now, if you see, when it comes to digital terminology, right, it is nothing but what we have. It is nothing but a group of flip-flops constitute a register, right? A group of flip-flops constitute a register. Now we know that flip-flops acts as a 1-bit memory element. It stores 1 bit of storage. It is nothing but the flip-flop is nothing but a 1-bit storage device. How it acts as a memory element? We know that when the clock input is applied, depending on the input, the outputs will be generated, right? And the outputs of the flip-flops will be holding on to that value till we apply the next clock pulse, so that it is holding on to the values till the next clock pulse is applied there, so that it is storing a value of 0 or 1 till the next clock pulse is applied. And that's how it acts as a 1-bit memory element. The flip-flops acts as a 1-bit memory element, so that when I say 1 bit, it can store a value of 0 or a 1. And registers are nothing but what? It is nothing but a group of flip-flops, right? It is nothing but a group of flip-flops. So that now when I say a n bit register, like take an example, yeah, I just interchanged here. This is n and this is b, right? A n bit register has a group of n flip-flops and is capable of storing any binary information containing n bits, right? It means that if I want to, when I say 4-bit register, when I say 4-bit register, what you understand by that? How many flip-flops do we have it there here? It means that we should have 4 flip-flops so that it contains a binary information of 4 bits here, right? And also there are register which we call it as a shift register, a register which is capable of shifting its binary information either to the right or to the left. We call that as a shift register here. I'll explain this one as we proceed. As of now, just remember what you mean by a shift register. If you can shift the binary information, whatever is stored in the register or in the flip-flop to the right or the left, we call that as a shift register, right? And we have something called as a unidirectional and bidirectional. When I say unidirectional, it means that we can shift the data either to the right or to the left. When I say bidirectional shift register, we can shift to the right or the left. We can perform both the right and left shifting. When I say unidirectional, you can shift it in the either in the right or in the left direction, right? I'll explain this one as we proceed, so that when I explain different types of shift registers we have it, I'll explain this. I'll try to cover this more, right? Everyone understood this one? What register is nothing but a group of flip-flops, and flip-flops are capable of holding 1 bit of information. Yeah, the transfer of new information into a register is referred to as loading the registers, right? We studied about the D flip-flop. What we do, we apply the input there. For D, we give a value of 0 or 1, and when you apply the clock pulse, if the D is 0, what will happen here? That value will be loaded, and depending on the input, depending on the behavior of the flip-flops, the output will be generated there. This we call it as what? The new information, which is the transfer of new information into a register. We call it as what? The loading the register, right? And there are 2 basic ways in which information could be entered into and outputted from a register. What are the 2 methods we have? Serially we can enter the data, and serially we can take the data output from a register, and we can load the data parallel, and similarly we can get the output parallelly, right? There are 2 methods. One is serial and the other one is the parallel way of entering the data or getting the data from the register. What do you mean by serial here? The serial handling of information involves symbol by symbol availability of information in a time sequence, right? What you understand by this one, it says serial handling of information involves symbol by symbol, like here bit, right? It means that at any point of time, only 1 bit of information is loaded onto the register, or at any point of time, 1 bit of information to get from the register here, right? That we call it as a serial way of transferring the information here, right? Everyone understood this one? When I say serial here, it means that 1 bit of information is transferred. The 1 bit of information is manipulated here, right? The transferred and manipulated at for a single clock pulse. For every 1 clock pulse, 1 bit of information is loaded onto the register, or 1 bit of data, what you get as an output from the register. You call that as a serial transfer, right? Next, what we have is a parallel. What do you mean by parallel here? As it is written in the description, all the 0, 1 symbols that comprise the information are handled simultaneously as an entity in a single unit of time. It says as an entity. Entity is nothing but a group, right? It is considered as a one group here, as an entity. It means that all bits of informations and all means it means that simultaneously we can load the data onto the registers, and simultaneously we can receive the data from the register in a single clock pulse. We call that as what? Parallel transfer, right? I'll explain this one when we go to the shift register, different kind of shift registers, right? Serial, parallel, data transfer. I'll explain this one in a while. Right? Everyone understood this one? What do you mean by loading of the registers here? It is nothing but the transfer of new information into a register. And there are two different ways by which how the data could be entered, or we can take the data out from the register. The first method is serial. The second one is parallel. When I say serial, it means that at any point of time, only one bit of information could be entered, or we can get one bit of information out from the register, right? And what do you mean by parallel? Simultaneously. It means that simultaneously we can load more number of bits, right? Bits onto the register, and simultaneously we can get the output from the register here, right? In the same single clock pulse. This is about the parallel. Yeah. Now, since we studied, there are two ways by which how we can transfer into the register, and we can get the data from the register. So that since there are two ways, so that how we can have it, we have input output, and there are two ways, serial and parallel. How much we get? 2 raised to 2 is 4. There are 4 different ways how the data could be entered, right? You can see here, and how the data could be taken from the register. The first one what we have is serial in, serial out, serial in, parallel out, parallel in, parallel out, parallel in, serial out. In today's class, we'll study about the first two ways how the data could be transferred, right? The first one what we have serial in, serial out, and the second what we cover will be serial in, parallel out. Yeah, this is a 4-bit register or 4-bit shift register what we can, because each flip-flop is capable of holding a value of 1 bit of information. So that what we have, there are 4 flip-flops, so that it is 4-bit register, and it is 4-bit shift register. Why it is shift register? Because for every clock pulse, whatever the data we have, that is shifted from one register to the next register here. I can see from this one we have a clock input which is given to the all the 4D flip-flops what we have it, right? And if I want to give the data here, right? The serial data has to be given to the first flip-flop, and for since it is serial in, parallel out, and we take the output from the last flip-flop what we have it. Take an example now. I'll call this one. This is Q0. This is Q1, Q2, and this is Q3, right? And as I said here, when I say serial, what you understand by that? We load 1 bit of information for a clock pulse. Now we apply the clock pulse here, right? Now we have the clock pulse. Assume that the previous state what we have it, so whatever is the previous state what we have, maybe we assume that this is equal to 0, this was 0, and this was also 0, and this is also 0 here, right? Now I apply the clock pulse, and I give the input as 1 here, right? Now when I apply the clock pulse, since it is a D flip-flop, what will happen? Whatever is an input, that will come as an output here. Now since this is acting as a shift register also, right? So that whatever is the value here, 0, that is given as an input to the next flip-flop. Since this is 0, what we have, this is 0 here. Similarly, what we have it here, this is 0, what we have it, this is 0, and this is 0. The data been shifted here, right? I'll just give one. I don't know whether you can see this one screen here. Hope everyone can see the white screen here. Okay, the whiteboard is shared here now. I don't know why it is still showing that annotation here. Okay, what it may be. Now we'll see that this is, we call it as a serial data. I call it as DS. What we have is, this is Q0, Q1, K3, this is Q3 here, right? Now I have not applied any input here, and we'll assume that this is holding on to value of 0, 0 now, right? 0, 0, maybe if it is 0 here, right? The clock pulse is applied, right? Now what happened, the input, now the input is what we have it, this is 1, right? And the clock pulse is applied. Now what will happen here is, now here you get this as 1, and whatever now it has access shift register, the data is shifted. And this data what we have for the Q3, that is lost. This data is lost here. Similarly, if I apply the next clocker and the D input, I will have 0. So that what we have now here, this is 0. That will be 1. Now this is shifted here. 0. This is be 0 here. Right. Now again apply the clock pulse. And this is 1. So that what we get now here, 1. And this is shifted here, 0. This is shifted 1. And this is 0. Right. Everyone can relate with this one. Similarly, apply the clock pulse. Now it is 0. So that what we have, 0, 1, 0, and 1 here. Now you can see this one, right? What we have it here, we have 1 here, right? Now I keep on applying the clock pulse, so that what we have now, we get it as 0. So that we have 1 here, we get it as 1. Here we have 0. So that when I apply the next clause, you get it as 1. So that now this is what we applied. For every clock pulse, we have loaded 1 bit of information onto the register here, and we are getting that 1 bit of information. Here it is 0 here, right there. So that output also what we have, for every clock pulse, we are getting the whatever the serial data we have given here, the same information we are getting as an output of the third, the Q3, the output Q3 what we have. So here it is 0, here have 0 here. It is 1 here, we have 1 here, 0 here, and 0 here, right? Yeah, this you call it as what? Serial in. It means that for every clock pulse, we are loading 1 bit of information onto the register. Now here what is happening here? For every clock pulse, we are getting 1 bit of information as an output from the register, right? So that this kind of combination, what you see in the diagram, this we call it as a serial in, serial out, shift register. It is acting as a shift register. And what kind of shift register is this one? Serial in, serial out. Why it is called as serial in? Because for every clock pulse, we are loading the register with 1 bit of information, and for every clock pulse we are receiving, we're getting the output, 1 bit of information as an output from the register here, right? This is called as a serial in, serial out, shift register. Right? Everyone understood this one? Serial in, serial out register here, right? So that, let me know if you have any doubts so that we can discuss offline. Next, what we have is serial in, parallel out. Again, it is unidirectional here. I've not mentioned here because the data is shifting in this direction. Unidirectional shift register. Now, what kind of shift register is this one? Serial in, parallel out, shift register here. Now, if you see the same diagram, what we have it here, if I want to emphasize that one. Now, if you can see that, I don't know, I'll just clear this one so that now what we have, it is serial in. It means, what do you mean by serial in here? It means we are loading 1 bit of information here. Q0, Q1, Q2, and apply the clock pulse here. If it was 0, we have 0, 0, 0. We will assume that the clock pulse is applied. Now this is 1. After the clock pulse is applied, we have 1, 0, 0, and 0. Similarly, now when I apply 0, what we get? 0 here. This gets shifted, right? 1, 1, this is 0, and what we have is 0. Similarly, if it is 1 here, what we get? 1, 0, 1, and 0 here. Similarly, what we have, apply 0 here, what do you get? 0, 1, 0, and 1 here. Now here, if you can see that we have loaded the registers with 1 bit of information for every clock pulse. For every clock pulse, we loaded 1 bit of information here, right? Right. Now you can see here, after how many clock pulse? After 4 clock pulse, you can see here, what is the output? We have it here now. The whatever in front, 1, 0, 1, 0. What we have? 1, 0, 1, 0, right? The whatever the serial data is entered here after 4 clock pulse, simultaneously we can see the 4 bit of information here, Q3, Q2, Q1, and Q0. This we call it as a parallel out. This is nothing but parallel out. You can see that after the 4th clock pulse, you have this data output which is generated at the register outputs Q3, Q2, Q1, and Q0 here. This is called as a serial in because 1 bit of information is loaded for every clock pulse as a serial in here. Yeah, that's what I'm trying to say. We have serial in here. We have serial in here. We keep on loading the values here. Right? If it is 1, what we get here is 1, 0. Take assume that this is 0 and 0. Next, what I load now? Load the value with what now? 0. So that this will be 0. Right? I will write it in this way. So that this is 1, this is 0, and this will be 0. Next, I will load the value with 1. So that what you get now? 1, and this data gets shifted here, 0, and this data gets shifted 1 and 0. Now I apply value of 0. And apply value of 0, what you get now here? 0, 1, 0, and 1. And the 4 bit of information, whatever is entered, right? We had 1, 0, 1, and 0. So that what we have? 1, 0, 1, and 0. Right? This we call it as what? Serial in, parallel out. All the 4-bit, we have it as an output here at QA, QB, QC, and QD. This is nothing but Q3. You can take it this way. This is nothing but Q. No. This is serial in, parallel out, unidirectional shift register. Why it is called as unidirectional? Because you can shift from here to here. The data is shifted from this flip-flop to this flip-flop, and here to here. And whatever the data you have it in Q3, you keep losing that data here. Right? Yeah, this is about the serial in, serial out shift register, and also serial in, parallel out shift register. In the next class, we'll study about the other two transfers what we have. What are the other two we have? Just a minute. Next, what we have it now? What are the other two possible ways of transformation of information? Parallel in, parallel out. The other one is parallel in, serial out. Okay, everyone, thank you. We'll see in the next class these two topics. Yeah, since we studied about serial in, serial out shift register, and also serial in, parallel out shift register, I will explain the same. What I already explained how it works. Now I'll show the demo through this simulation. We're using the tool Logic Sim. With the help of this tool, I'll explain how the serial in and how this serial in, parallel out, and serial in, serial out, the shift register works here. Now we have a clock here which is connected to all the 4 flip-flops, the D flip-flops what we have, and we have the outputs here, right? And this is nothing but the Q0, Q1, Q2, and Q3 here, right? And the data, you can see here, the data what we have is 0, 0, 0, right? Now what I do, I'll change this value. Now it is 1, and now I apply the clock pulse. Once I apply the clock pulse, you can see here that value, since it is D is 1, the output will be 1 here, right? Now we have 1, 0, 0, and 0. Now I'll make this as 0, right? Now since this is 1, now you can see here the output of the first flip-flop is, which is Q0. Q0 is equal to 1. Now that acts as an input to the next flip-flop. So that what we have D1. If you call this as a D0, D1, D2, and D3 here. So the what is D1? D1 is 1. So when it is 1, when I apply the clock pulse, what will happen? This will change to 1 here. And now this Q1 is nothing but it acts as an input to the next flip-flop. So that D2 is nothing but 0. So that when the clock is applied, what will happen here? Whatever, since D2 is 0, the output will be 0, right? And as I said here, this Q2 output what we have 0. So when the clock is applied, what will happen here? So that this will be 0. So that after the clock pulse, this will get it as 0. That is how it is acting as a shift register, because the output of the previous flip-flop is nothing but an input to the next flip-flop, and that is how the data have been shifted from one register to the other, or one flip-flop to the other here, right? Now apply the clock pulse, so that what we have 1, 0 here, right? We have 0 and 0. And again I'll change this value to 1 now. Again apply the clock pulse. What we have 1, 0, 1 here, right? Now I'll make this as 0. So that what we have. Now what we have now, this is nothing but what? For every clock pulse, we have loaded the value, 1 bit of information into the register. First we loaded the value of 1, right? You can see here, first we loaded the value 1. After that we loaded the value 0. After that we loaded the value 1. And after that we have loaded the value 0 here. Now what we have, for every clock pulse, we are loading 1 bit of information, so that you call this as a serial input, right? Now you can see here, after 4 clock pulse, we can see whatever the information I loaded here. I can see all the 4 bits of information at a time here. We have 1, 0, 1, and 0. This you call it as what? Parallel out. right? This is on the parallel out. Now you can see here, now how it is acting as serial out. The serial out, you take it from the Q3. Now it is 1. What you should get next here, 0. When I apply the next clock pulse, you should get here it as 1. Again, when I apply the clock pulse, you get it as 0. For every 1 clock pulse, you're getting 1 bit of information from the register. Right? So that now apply the clock pulse. What you get after 1, you should get it as 0. Now you get it as 0. Next, apply the clock pulse, you get it as 1. And next, what you apply, get as 0. So that what we got, 1, 0, 1, and 0. So that this is nothing but for every clock pulse, we are getting 1 bit of information from the register here. This is nothing but serial out. Everyone understood the concept of serial in? When I say serial in, it means the input is nothing but 1 bit of information. For every 1 clock pulse, we give 1 bit of information. When I say serial out, it means that we get 1 bit of information for every clock pulse. Right? When I say parallel, you can say simultaneously, we can see the 4 bits of information here. Right? This is about how the serial in, serial out, and parallel out works. Hope everyone understood this one.